In this video, we will talk about metric spaces. First, we will define what a metric space is and give several examples. Then we will talk about neighborhoods of metric spaces as well as examples. And last, we will talk about accumulation points and closures of sets and discuss how these concepts might differ from the real numbers in general metric spaces. We will start by defining a metric space. So let X be any non-empty set. A function D on X cross X that maps to R is called a metric on X if it satisfies the following conditions for all X, Y, and Z in X. D of XY is always greater than or equal to 0. D of XY is equal to 0 if and only if X equals Y. D of XY is equal to D of YX. And D of XY is less than or equal to D of XZ plus D of ZY, the triangle inequality. The set X together with a metric D is said to be a metric space, and we denote that with the XD. A couple of comments. So first, a metric space is a set along with an operation, a function. The function takes two elements from set X and maps it to a real number, and it must satisfy these conditions here. And essentially, a metric is an abstraction of the idea of distance, which is why this D is here, to kind of suggest distance. And as you know, the distance between 2 points is always greater than or equal to 0, and it's only equal to 0 if X and Y are equal. And then the distance between xy should equal the distance between yz. And then we also have this triangle inequality for distance. Our first example of a metric space comes from the absolute value metric on the real numbers. And this absolute value metric is the default metric of the real numbers. So if someone refers to R, the real numbers, as a metric space and do not specify a metric, we use the absolute value metric. And actually, the absolute value metrics is exactly your idea of distance, your normal idea of distance. All the other metrics are sort of abstractions of this idea. So in particular, we define the absolute value metric as the absolute value of x minus y. So dxy is equal to absolute value of x minus y. We can see that this metric follows all four conditions, which I have copied here. First, we know that x minus y is always greater than or equal to 0 because it's an absolute value. Second, the absolute value of x minus y is equal to 0 if and only if x equals y, because of how the subtraction of real numbers work. Third, we know that the absolute value of x minus y is equal to the absolute value of y minus x. And last, we have the triangle inequality. X minus y is less than or equal to x minus z plus z minus y. And this proof I am not going to do since it is done in a number of other places when you're looking at absolute values. Our next example is the Euclidean matrix, which takes elements from the set R cross R, that is, elements in a two-dimensional space. So the metric D is defined as the distance between the first point, x1, y1, and the second point, y2, y2, is equal to x2 minus x1 squared plus y2 minus y1 squared, all square rooted. In other words, this is what you commonly think of as the distance between 2 points in the R2 plane. And here I have some notes just outlining how the Euclidean metric satisfies the four conditions. And I left out the triangle inequality, again, because it's a bunch of algebra that I didn't want to do. And our last example is the discrete matrix. And we define the discrete matrix with this function here, d of xy is equal to 0 if x equals y, and 1 if x does not equal y. And you can see that it satisfies the four conditions because 1, it's always greater than or equal to 0, obviously, it's just 0 or 1. It's 0 if and only if x equals y, by definition. You can see that, you can see the rest. Anyway, and the interesting thing about the discrete metric is that any non-empty set can be made into a metric space with this metric. Next, we will look at the idea of neighborhoods in metric spaces. So we have had the definition of a neighborhood in the real numbers, but now we're going to look in a general metric space, XD, And we're going to let x, little x, be a member of the set x, and we're going to let epsilon be greater than 0, then the neighborhood of the element x of radius epsilon is given by, and then we have the notation, the capital N for neighborhood. The neighborhood of x with radius epsilon is all the y in x, so all the other elements in x, such that the distance between x and y is less than epsilon. And then the deleted neighborhood, which we denote with this asterisk after the capital N, is all the y in x such that the distance between x and y is between 0 and epsilon. A difference in the definition of a deleted neighborhood with the neighborhood is this, that the distance now has to be greater than 0. And what this does, it has the effect of eliminating the point or deleting the point x from the neighborhood, the deleted neighborhood. Our first example of a neighborhood is the absolute value metric, where D was defined to be the absolute value of x minus y. So our neighborhood then, we will define that as D of xy is less than epsilon. Plugging in our metrics, that means the absolute value of x minus y is less than epsilon, which I actually have this here, but I wrote it out here. So if x minus y is less than epsilon, that implies y minus x is less than epsilon, which is less than x minus y, which implies that y is less than epsilon plus x, so this portion of the graph, and y is greater than x minus epsilon, so kind of this portion of the graph. So what you get is this open interval centered at x with radius epsilon. So here is this picture and this here expression here, that the neighborhood of x with the radius epsilon is equal to x minus epsilon, the open interval x minus epsilon to x plus epsilon. Our next example is the Euclidean metric, which is defined on 2 points in R2, and if you recall, is your normal definition of the distance between the 2 points, x1, y1, and the point x2, y2. And if you look at the neighborhoods, if you define the neighborhood as the points x and y such that the distance between the 2 points is less than epsilon, taking this formula here, you can see less than epsilon. This is exactly the equation of the open disk, the inside part of a circle. Like, you can rewrite this here as an equation of a circle. And so, for example, if we have x equal to 0 and the radius equal 1, we get this disk of an open disk of radius 1. So neighborhoods are disks. And just a quick comment, I say the word disk instead of circle because circle is defined as all the points equidistant from a point, from a center. So that would be where these points are equal to epsilon. The disk is all these points inside, and open because it does not include the boundary, since this has no equality. Our last example will be the discrete metric. If you recall, that's equal to 0 if x is equal to y, and 1 if x does not equal to y. So for the neighborhoods, we are going to look at 2 cases, when epsilon is less than or equal to 1 and when epsilon is greater than 1. So by definition of neighborhood over here, we're looking for y in the set such that the distance is less than epsilon. So if epsilon is less than or equal to 1, we're looking for y in the set x such that the distance between x and y is strictly less than epsilon, which the maximum epsilon is equal to 1. So if we want to be strictly less than epsilon, that would be 0, and that's only the case if x equals y. So the neighborhood of x with an epsilon less than or equal to 1 is simply equal to x. Now let's consider the case where epsilon is greater than 1. So in this case, we're looking at the neighborhood of x. We're looking for y and x such that the distance between x and y is less than epsilon, but epsilon is greater than 1. So what that means is we're in this case over here. So it's all values of y that do not equal to x, plus we also have x because this is also within epsilon. So that means all of the set x is in the neighborhood. So we have this kind of binary thing. So the neighborhood, if epsilon is less than or equal to 1, is equal to x. If it's greater than 1, the neighborhood is the entire set. And I do want to warn you that the discrete metric, the idea of distance really goes against your intuition because, for example, on the real number line, I have 3 points x, y, and z, and normally you want to say that y is closer to x than z is. But according to the discrete metric, both y and z have the same distance from x, and the distance is equal to 1. Next, we have the theorem. If we have a metric space, any neighborhood of a point in the set of the metric space is an open set. So neighborhoods are open sets. And for our proof, to see that x is an open set, we shall show any point y in the neighborhood x of epsilon is an interior point of the neighborhood. We're going to start by taking y in the neighborhood. So we have y in the neighborhood of x with a radius of epsilon. Then we're going to define delta to be equal to epsilon minus the distance between x and y. And we know that this is greater than 0 by definition of a neighborhood, where epsilon is greater than the distance between any x and y. So that means epsilon minus d of xy still needs to be greater than 0. We claim that the new neighborhood around y with this delta as its radius is completely contained in the neighborhood of x with the epsilon radius. And if it's completely contained, then y is an interior point. And I have a picture to kind of show what's going on. So I just took an example of x, and I made epsilon equal to 4. So here is my disk, my neighborhood. And then I have some value y here. So here I have y. You can see that the radius is 1, 2, 3, 4. And y is, the distance between x and y is 3. So that means the radius delta now for this new neighborhood is going to be 4, the epsilon, minus the distance between x and y. And remember, the distance between x and y is always less than epsilon, right, just by the definition of neighborhood. So that means that this radius here around y will always be contained in the neighborhood of x. So while you can see in my picture sort of what's going on, we do need to prove formally that anything in the neighborhood of y with this new delta radius is also in the neighborhood of x with the epsilon. So let's say z is in our neighborhood of y with the delta radius, then the distance between y and z is less than delta. So the distance between z and x by the triangle inequality is less than or equal to distance between x and y and the distance between y and z. The distance between y and z, since z is in the neighborhood of y with radius delta, must be less than delta, strictly less than delta. So I've replaced my distance between y and z with delta. And now delta, over here, by how we constructed delta, is equal to epsilon minus distance between x and y. So now these two distances, because they're equal, because it's a metric space, that means we were left with epsilon. Thus, the difference between z and x is less than or equal to epsilon, meaning z is in the neighborhood of x with radius epsilon. Thus, we've shown that if something is in the neighborhood of y with the radius of delta, it is also in the neighborhood of x with radius of epsilon. So what we have is the neighborhood of y with delta is a subset of the neighborhood of x with epsilon, and y is an interior point of the neighborhood of x with epsilon. And so since it's an interior point, we can see that any point in the neighborhood is an interior point. Hence, by definition of an open set, the neighborhood of x with radius epsilon is open. Our first example, consider the set R2 with Euclidean metric. From chapter 3, we know the intersection of any finite collection of open sets is an open set. Find an infinite collection of open sets in R2 whose intersection is not open. In this case, what would be good, since we're intersecting and we don't want it to be open, we want to find an easy example would be to find a collection of infinite sets whose intersection is a single point. So any nested set of sets would be good. So for example, an is equal to the neighborhood 0 from to 1 over n. And just to draw what these nested sets look like, so A1 is the neighborhood of 0 with radius 1. So I have that in black. A2 is the neighborhood of 0 with radius 2. That's in blue. And A3 is the neighborhood of 0 with radius 1/3. And again, they're nested. In other words, each, as you get smaller, it's contained in all, as n increases, it's contained in all the previous A sets, all the previous neighborhoods. And so when you keep going infinitely, they basically intersect at a single point, 0. And the single point is not open. To be clear, all these neighborhoods are, because every neighborhood in a metric space is open, but the single point is not. And just a quick reminder of how you can prove that the singleton 0 is not open is you can look at its complement, which is negative infinity to 0, union 0 to infinity. These are two open sets, and the union of two open sets is open since it's complement. So basically, the complement of a non-open set is open. And so this is kind of, they're just kind of expanding on this statement here. In this next example, we are going to use the discrete metric in R over R2. Can you find an infinite collection of open sets whose intersection is not open? And you want to compare this to our last example. So for example, here I have 3 points in R2. I have x1, y1, x2, y2, and x3, y3. And you might be tempted to think that x2, y2 is closer to x1, y1 than x3, y3 isn't. But according to the discrete metric, these two, x2, y2, and x3, y3, are both 1 unit away. They're equally distant from x1, y1. So you have to be very careful with the discrete metric and use the definitions, maybe not so much your intuition, but unless you have better intuition for this than I do. So here's our discrete metric, and just to kind of look again at our neighborhoods, so if we were looking, centering our neighborhoods at 0, 0, and we look at epsilon equal to 1, so we want the distance between our point y1 and y2, basically it's all the points y and r2, so y1, y2, that their distance from 0, 0 is less than 1, right, if epsilon is equal to 1. And here, the only points that have a distance less than 1 is when the distance is 0, and that's when x1, y1 is equal to x2, y2. In other words, when y1, y2 is equal to 0, 0. So it's our singular point 0, 0. For neighborhoods centered at 0, 0 with radius 2, now we're looking for points y, or y1, y2, such that the distance between 0, 0 and y1, y2 is less than 2. And that is everything, because at most, everything is at most 1 unit away. So this neighborhood is equal to R2, because every pair of points is at most 1 unit away. Now we are ready to look at our question. So we're looking at open sets. And just to remind you what an open set is, again, because now we have to kind of use our definition of discrete metric take it very literally. So S is an open set if all points in S are interior points. There are many definitions and many criteria you can use, but this is the one that I like. It's an open set if all points of S are interior points. So you can draw a neighborhood around each point that does not intersect anything outside of S. If it's an interior point, you can draw a little neighborhood around it without going outside of S. And you compare this to a boundary point where every neighborhood of a boundary point contains elements in S and elements outside of S, which is kind of what you would intuitively think of a boundary. So finally, the answer to the question, can you find an infinite collection of open sets whose intersections is not open? And it is not possible to find such a collection because every subset of R2 with the discrete metric is an open set. And this is really important. This is a fact you want to remember. Every subset of R2 with the discrete metric is an open set. And the reason is, if you take any point in R2, we always can find a neighborhood, P with epsilon equal to 1, around RP. So there's always this neighborhood around P that does not contain any other element. It only contains P. So we're not intersecting, we're not on the boundary and overlapping with something else. So every point we can draw a neighborhood around it. So, so basically each singleton set consists of one point, and we can have an open set. So every set is the union of open sets, therefore every set is open. Let's take one more comparison of a singleton point. So let's say we want to consider the point x1, y1, and why this point is open in the discrete metric, but this single point is considered closed in the Euclidean metric, in the Euclidean spaces. And so let's look at this drawing here, x1, y1. So if I want to consider a neighborhood, I can draw a little neighborhood around x1, y1. If I'm in the Euclidean, using the Euclidean metric, the Euclidean space, then there's no way I can draw a neighborhood that, no matter how tiny, that won't include some other ordered pair, x2, y2, well, or in this case, x4, y4, because there's real numbers, they're really dense right here. So like there's just no way I can draw another little neighborhood around x1, y1 that doesn't include other points outside this set. And for that reason, when you use the Euclidean metric, a single point is closed. However, with the discrete metric, there's lots of space between all the points that aren't equal to each other. So if we draw a little neighborhood around this, we can, as long as our epsilon is less than 1, we can always do that around any singleton point. So that's the difference here between the singleton point. It's open in the discrete, using the discrete metric. It's closed using the Euclidean metric. Isn't that kind of strange? But there you go. Next, we're going to talk about accumulation points. And just to kind of review what an accumulation point is that X is an accumulation point of a set S if for every epsilon greater than 0, the deleted neighborhood of X with radius epsilon intersect S is not empty. So in other words, if X is an accumulation point, no matter how small a neighborhood you draw, you'll always find an intersection with S. Any neighborhood of X will always intersect S. So in other words, no matter how tiny of a neighborhood you have, you intersect S, so X in some sense cannot get away from S. As opposed to Y, here Y is not an accumulation point, and obviously you can draw some sort of little neighborhood here that does not intersect S. So Y is able to get away, but X can't even get away just for the tiniest, smallest epsilon. It's always close to S. We also had the closure of a set S, so the closure of set S is equal to S plus S prime, where S prime is its set of accumulation points. We have this theorem for the real numbers, but some of the things are going to be a little different now for our metric space. We are going to start with the definition of a bounded set S in a metric space. So a set S in a metric space, XD, is bounded if S is a subset of some neighborhood N of X epsilon. So we'll start with saying X, our space, our set for the metric space, may not be bounded. So for example, R or R2 is not bounded, it goes to infinity. But if for some set S in R2, you can surround it by some neighborhood, then if you can encapsulate it with some neighborhood, and you know, depending on where S is, you might choose this X here, and then you might have this epsilon, right? Or you might choose this X over here, in which case your epsilon might need to be bigger. But the idea is there's some X and there's some epsilon that will totally encapsulate your S. So again, X for the metric space may not be bounded, but a subset of the metric space set S might be bounded. And I have this definition moved up here for a bounded set S in a metric space. And we have this theorem, let S be a compact subset of a metric space, then 1, S is closed and bounded, and 2, every infinite subset of S has an accumulation point in S. So compact will imply closed and bounded, but the converse is not necessarily true. This is not an if and only if. The proof of these two statements first relies on the first half of the Heine-Borel theorem, and I believe the second half of the Heine-Borel theorem does not apply to all general metric spaces. And then the second part depends on the Bolzano-Weierstrass theorem. Our next example is a little discussion. Let's consider R2 with the discrete metric. And we saw earlier that every subset of R2 with the discrete metrics is open. And this is really strange. Since the complement of an open set is closed, this means every subset is also closed. So let's consider S be the unit square, which I have defined here. Clearly S is bounded. Again, bounded means you can have some a neighborhood around your set. So since it's a unit square, we can just draw a circle of radius 2 and it'll cover our entire unit square. But S is not compact because, and let's review the definition of compact. Here I have our condition of compact set. So a set S is compact if whenever it is contained in the union of a family of open sets, it is contained in the union of some finite number of sets in F. So in other words, if we have an open cover for our set S, and an open cover is a set of sets whose union contains S. So if we have an open cover, then we can find it's compact if and only if for every open cover there contains a finite subcover. So let's see that S is not compact. So let's take each point in S. So we can have a cover for S, AP, is equal to this the point P. Then each P is an open set. Remember, in the discrete metric space, every subset is an open set. So then each AP is an open set, and S is a subset of the union of all of these AP. So here we have an open cover of an infinite open cover of S, basically all of the individual elements. However, there's no finite subcover of S since each AP only contains one element, and the set S in R2 contains an infinite number of elements, which means you need infinitely many APs to cover the set S. So we conclude in this metric space the unit square is closed and bounded but not compact. So we've completed the topics of this video. We first talked about metric spaces, we talked about neighborhoods of metric spaces, and then we talked about accumulation points and closures and how metric spaces may differ from the real numbers at this point. Now for review, I have 2 problems for you to try. So pause the video, give the problems a try, and on the next slide, I'll have solutions for you. And actually, problem number 1, I think we did this proof already, or at least we discussed everything involved in it. So here are the solutions to the 2 problems. And that's it for this video. Thank you for watching.